Very exciting celebration coming up. Woohoo! Wait till we get about 25, 30 people, and then I will start. Oh. Let me just pop this up while we're doing this. Why is that not doing something? PowerPoint slide. That's what this. All right. So let me mute everybody for a second. All right. So what I want to do is pretty much just finish chapter 11. And then we'll be set with everything for the celebration on Wednesday. So what I'm going to do is just start off with a little recap and then finish the last parts of chapter 11. And then tomorrow I'll sort of give you a little bit of review, give you an idea of the kinds of problems you can expect in terms of the overall difficulty for the second celebration. So let me share this. Okay, so as a little reminder, forces generally are not constant, even though we have been modeling them as constant. During any kind of collision in general, if you were to plot the force versus time, what you would see is, let's get a new color here. Let's go with green. So the force starts at 0, increases to some maximum value, decreases back to 0. We define the impulse as basically the overall effect of the force versus time. So impulse is defined as the integral of the force with respect to time. So conceptually then, the impulse is the area under the curve of force versus time. Now, oftentimes, rather than looking at the area under the curve, we want to look at something with the average force. So the average force is defined as a constant force. Even the force is not really constant, but it's the constant force acting over the same time that would give you the exact same area under the curve of the real force. So like in this little example here I drew, in red might be, let's say, the collision of a bat with a ball. And this is what the force really looks like. But I can also say that the impulse is the average force times the time over which it acted. So in terms of a little recap. So impulse, we give it the symbol J, and it's defined as the integral of the force with respect to time. So impulse is the area under the curve of force versus time. Another way of writing it is it's the average force times the time over which that average force is acting. The units of impulse are the Newton seconds, which is the same thing as a kilogram meter per second. Momentum is a quantity that is a vector, and it's defined as the mass of an object in kilograms times the velocity in meters per second. Momentum is a vector, and it has the exact same direction as the velocity of the object. The units of momentum, kilogram meters per second, no special name for it. Impulse momentum theorem says the following. The impulse on an object will equal the change in momentum of that object. And since impulse and momentum are both vectors, then if I want to know how much does the momentum of an object change, let's say in the x direction, then what I'm looking at is the impulse in the x direction, which is the integral of fx dt. That's big thing, impulse momentum theorem. Impulse in an object equals change in momentum. Other thing I started looking at is conservation of momentum. And what I first talked about was that Newton's second law, when he first published it, he didn't publish it in the form F equals ma. The way he actually published it was the sum of the forces on an object equals the change in momentum of the object with respect to time. Momentum is mass times velocity. So if I do d dt of mv, I have to use the chain rule. So what I get is m dv dt plus v dm dt. So we are pretty much ignoring any changes of mass. So any system that we look at, we're assuming the mass doesn't change. So this dm dt term is 0. So the sum of the forces equals ma. is the same thing as the sum of the forces equals the change in momentum with respect to time if I assume the mass of the system or the object doesn't change. And then the last thing we looked at, if I have a system of objects, again, you can define the system however you want. The total momentum of the system would just be the sum of the momentum of all the different objects in the system. I've got 5 objects in the system. Total momentum is I just add the momentum of all 5 objects. Just like when we were looking at energy, we define our system. Anything that's not the system is the environment. Internal forces are forces objects within the system exert on other objects within the system. External forces are forces the environment exerts on the system. So what I can say is for a system, the sum of all the forces acting on the system equals the change in momentum of the system with respect to time. And I can classify the sum of the forces, I can break it up into 2 different sets. I've got internal forces and I've got external forces. So when I say the sum of the forces on a system, now what I'm just doing is rewriting it as there's 2 kinds of forces. They're either external or internal. And because of Newton's third law, if I have one object exerts a force on a second object, that second object exerts the exact same force on the first, exact opposite direction, which means by Newton's third law, the sum of the internal forces always has to be 0. So I can completely ignore this sum of the internal forces. And what I get is the sum of the forces on a system, all the external forces acting on a system, I add them all up, and that equals the total change in momentum of the system. So conservation of momentum is really just a consequence of this. And what it says is, if the sum of the external forces is 0 in a system, the change in momentum of the system with respect to time is 0, which means my final momentum equals my initial momentum. So if the sum of the external forces is 0, momentum doesn't change. And keep in mind that momentum is the total momentum of the system, which I have to add all the momentum of all the objects together. So just real quick, we're going to cover today. I want to quickly just give you a relationship between momentum and kinetic energy, because sometimes you want to know one versus the other. We're going to talk a little bit about collisions, 3 different kinds. Perfectly elastic, inelastic, perfectly inelastic, and then we're just going to talk a little bit about explosions. So what I want to do is just pause this for a second and then open it up for a quick little question or 2 about anything that I've covered so far in terms of momentum, impulse, anything like that. Questions, questions, questions. Going once. Going twice. Sold for no dollars. Okay, let's go back to this share. And I want to talk a little bit just about the relationship between kinetic energy and momentum. So, just real quick, we know that kinetic energy is just 1/2 mv squared. And if I just look at the magnitude of the momentum, not considering the direction, the magnitude is just the mass times the velocity. So if I write kinetic energy as p squared over 2m, what you'll see is this is just mv squared over 2m, which is basically the same thing as 1/2 mv squared. So a nice little relationship between kinetic energy and momentum is, in terms of the magnitude, kinetic energy is given by p squared over 2m, or the momentum of an object is the square root of 2 times the mass of the object times the kinetic energy. Okay, so given that, I have a couple questions I'd like to go through. That's not it. Oh yeah, let's do this. First question. This is conceptual question 11.4, and it says this: a 0.2 kilogram cart and a 20 kilogram cart can both roll without friction on a horizontal surface. Equal forces are used to push both carts for a time of 1 second starting from rest. After the force is removed at 1 second, is the momentum of the plastic cart greater than less than or equal to the momentum of the lead cart. So two different carts, one has 100 times the mass of the other. I exert the same force for the same time on each, and the question is, how do the momentums compare? How does the momentum of the plastic or lighter cart compare to the momentum of the heavier cart? Take about 20 seconds, think about that. What do you think? How do the momentums of the two carts compare? And I'm going to start writing out the answer. And the answer for this particular one is equal to. Why? You're told you exert the same force for the same amount of time, which means you exert the same impulse on each, which means the change in momentum of each one has to be the same. Well, they both started from rest, which means the initial momentum of each is 0, which means the impulse that I apply to each has to equal the change in momentum of each. So if they both started from rest and this impulse on each one is the same, they have to have the same final momentum. So the answer is equal to. Now, in terms of Newton's second law, the object that has 100 times more mass is going to have 100 times less acceleration, which means at the end of the force being applied, if it started from rest, it'll have 100 times less velocity. But keep in mind, momentum is equal to mass times velocity. So the object that has 100 times as much mass is going to end up with 100 times less velocity just because the acceleration will be 100 times less. So easiest way to think about this, same force over the same time produces the exact same impulse, which means the change in momentum of both objects will be the same. And if they both started from rest, that means they both have to end at the same momentum. So second one, same concept, but a little bit different. A 0.2 kilogram plastic cart and a 20 kilogram lead cart can both roll without friction on a horizontal surface. Equal forces are used to push both carts forward a distance of 1 meter starting from rest. First case, we push both carts for 1 second. Now we're pushing both carts over a distance of 1 meter. And now the question is, now how does the momentum of the plastic cart compare to that of the lead cart? So first case, we applied the same force for the same amount of time. Second case, we're applying the same force over the same distance. And now the question is, how do the momentums compare? Take about 30 seconds. It's a little bit more challenging than the first one, but think about how can I use work and energy to possibly answer this question. And again, I'm going to start writing out the solution. And let me just change colors here. Draw. Let's do this in red. So in this case, we're applying the same force over the same distance, not the same time. Remember, work is defined as the integral of f dx. So if I apply the same force over the same distance, I do the same amount of work. And remember, the work on an object equals the change in kinetic energy of the object. So if I do the same amount of force over the same distance, I do the same amount of work, which means the change in kinetic energy each will be the same. But it didn't ask for how much the kinetic energy changed. It wants to know about the momentum. So what we now know is the kinetic energy of the carts, I'm sorry, what do we have? Plastic and lead. Kinetic energy of the plastic cart is going to be the same as the kinetic energy of the lead cart. But we want to know, how do the momentums compare? Well, since the work done was the same the change in kinetic energy is the same. Since they both started from rest, they're both going to end with the same kinetic energy. But remember that momentum I can write as the square root of 2 times the mass times the kinetic energy. So if they both have the exact same kinetic energy, whichever one has the smaller mass is going to have less momentum. So in this case, I want to know, is the plastic cart's momentum greater than, less than, or equal to? In this case, the plastic cart is going to have less momentum. They're going to end up with the same kinetic energy because the same amount of work was done. But two objects with the same kinetic energy and different masses, the one with the smaller mass is going to have less momentum. All right, let me just pause that. Open that up again. So keep in mind, impulse is force, integral of force dt. Work is the integral of force dx. Impulse in an object equals the change in momentum. The work on an object equals the change in kinetic energy. All right, let me pause. Any questions I can answer on that particular example questions?
Can you show us the board that you were writing on again?
I
just
can.
Didn't have a chance to like really write it all down. And
right here?
Yes.
Yeah, so keep in mind, this part, conceptual question 11.4, we had the same impulse, which means we had the same change in momentum. Since they both started from rest, they both ended with the same momentum. The second question, we had the same work, which means they both end up with the same kinetic energy. But we were asked about momentum. And again, a nice relationship to remember is for kinetic energy, it equals the magnitude of the momentum squared over 2m. And then for momentum, it's the square root of 2mk. So for this case, they had the same kinetic energy, but this object with the smaller mass then would have the smaller momentum.
Are those two equations just the two that you had written up above before doing these example problems?
So I didn't write the first equation. So the first one was basically just the impulse on an object equals the change in momentum. The one that I didn't write from before is the work on an object, which equals the integral of f dx equals the change in kinetic energy. So impulse, force and time, results in a change in momentum. Work, which is force and distance, results in a change of kinetic energy. Okay, let me do an example problem. Do I want to do one? Actually, let me just make up one just as a classic example. So let's say I had two people on a frictionless ice surface. And let's just call the mass of one 50 kilograms. The mass of the other one is, let's just call it 100 kilograms. They're both at rest. And now one person pushes off the other person. And as a result, let's just say this guy is moving backwards, afterwards at, let's just say -5 meters per second. The question is, question is, how fast would this person be moving afterwards? So you got two people at rest. They are sitting on a frictionless pond, let's say an icy pond. They push off each other. The person with a mass m1 ends up moving to the left at 5 meters per second afterwards. How fast is the person of mass m2 moving? So the way you do these momentum problems is this. First, you define your system. And keep in mind that the reason this is important is because as long as the sum of the external forces on a system is 0, then the momentum of that system is going to be conserved. So for my system, I'm just going to call it the two people, m1 and m2. So if that's the case, the external forces are any forces that these people are not, any forces coming, The system of my two people, which means the forces they exert on each other are internal forces. Gravity is an external force, the normal force is an external force. So the external forces on the system are basically the normal force on each and gravity. But as long as there's no acceleration in the y direction, the normal force is going to equal the force of gravity on each person, which means that the sum of the external forces on this system is 0, which means my final momentum is going to be equal to my initial momentum. Well, in general, the momentum of a system is just the sum of the momentum of each object. So in this case, if I have two objects, the total momentum of my system will just be the mass of one times its velocity plus the mass of the second object times its velocity. So in this particular case, they both start at rest, which means the initial momentum is 0, which means if the sum of the external forces is 0, then the final momentum has to be 0 also. So what I'm going to get from this is my final momentum, I can write as m1 v1 final plus m2 v2 final. And let's just be specific. How would I write my initial momentum? It would be m1 times v1 initial plus m2 times v2 initial. But they are both initially at rest, which means that the initial momentum of each is 0. So basically, if the initial momentum was 0 and the sum of the external forces, the sum of the external forces is 0, momentum's not going to change. So what I get is m1 v1 final plus m2 v2 final equals 0. And what are we looking for in this case? We're looking for how fast the second person m2 is going afterwards. So we're solving for v2 final. So what I get is v2 final equals negative m1 v1 final over m2. And then just plugging in our values. What did I say? m1 was 50, v1 final is negative 5. So this is going to be negative 50 kilograms. They are moving to the left. Important point. When you're doing conservation of momentum problems, if an object is moving to the left, its velocity is negative, which means its momentum is also negative. But you have to remember to include a minus sign if you have objects that are moving in opposite directions. So my velocity, since it's moving to the left, is negative 5 meters per second. And then I'm dividing by the mass 2, which is 100 kilograms. So what do I get? I get 250 divided by 100. So what I get is 2.5 meters per second. That's how fast m2, the second person, is moving to the right. Notice the velocity came out to be positive because the person is moving to the right. So the nice thing about this is trying to use Newton's laws to calculate something about how fast they're moving is challenging because I don't know the exact force that each person exerts on the other person. But here's the beautiful thing about momentum. Momentum is always, always conserved in any kind of collision or interaction where the objects are only exerting forces on each other and all the external forces add up to 0. So I don't need to worry about what force the other person exerting on the second person. It's an internal force, which means the total momentum of this system of two people is not going to change. Okay, let me stop that for a second. Actually, let me do one more. What do I want to do? Let me just touch on what did I want to go through. Okay, so let me just talk a little bit about the definitions of the different kinds of collisions. And let me just be specific about, I'm going to talk tomorrow about sort of the level of the problems, but the celebration is going to be 25 questions, half of them about multiple choice, the other half will be sort of problems, but the problems will be sort of like the problem I just did, at most 1 or 2 sort of relatively straightforward steps. Okay, so in terms of collisions, there's 3 main kinds of collisions that we sort of tend to look at. One, let me just, is there a chat question real quick? Chat. Why can't I pull this up? What about extended time? So those of you who have extended time on the celebrations, I will deal with that today. Just so you know, you have 3 full hours for the celebration. It's only 25 questions. You should have plenty of time, but those of you who have accommodations, I will add those. Okay, so let me just, before I do collisions, talk about explosions. And one of the reasons why momentum is so valuable is, let's go to a new section here. Let's say I had a firecracker just in space. Firecracker. If this firecracker is at rest, then the total momentum of the firecracker is 0. If I define my system as basically just the firecracker and everything in it, then here's the thing. Whatever causes the explosion, since it was internal to the firecracker, whatever caused the explosion is going to be an internal force. So if I define my system as just the firecracker, and let's say it's out in space far from anything, then there's going to be no external forces, which means whatever caused the explosion is an internal force. So in this case, the sum of the external forces would be 0, which means that the change in momentum of the system would be 0, which means if this firecracker started off at rest, it has no momentum at all. So after the explosion, let's just say that this thing exploded into 4 pieces. And these pieces could have different masses, but these pieces are all going to be moving in different directions. But if I were to add the total momentum of those 4 different pieces together, what I would find is if the total momentum of the firecracker started off at 0, it's going to remain at 0 even after the explosion, because what caused the explosion is an internal force. So this thing explodes into 4 pieces. Since momentum is a vector, I'm going to have just as much momentum pointing up as I do pointing down, just as much momentum pointing to the right as I do pointing to the left. The total momentum is going to remain at 0. The other nice thing about momentum, and I really wish we were able to do a lab with this, is in any kind of collision, and let's just say a collision between 2 objects, here's the thing. Momentum is always conserved, even when energy is not. And this is why momentum is such a powerful concept in physics. If you continue on in physics, at some point you'll start looking at particle physics. The way we know much about the universe, it's just by these particle accelerators that take these beams of maybe protons and antiprotons, electrons and positrons, speed them up to near the speed of light, and then crash them together. The way you analyze these collisions is basically using conservation of momentum as one of your main tools, because in a collision, total energy could be conserved, but anytime 2 objects physically do touch and collide, heat is going to be generated. And it's really challenging to figure out exactly how much heat is generated in a collision. But here's the beautiful thing. Momentum is still going to be conserved in a collision, because any forces the objects exert on each other are going to be internal forces that aren't going to affect the total momentum of the system. So just in terms of collisions, let me just say that we generally talk about 3 different kinds. And I'm going to tell you, I'm not going to test you on perfectly elastic collisions. There's a couple equations in the book that even when I teach this live, I don't derive just because it's a couple pages of algebra. So your problems for this will be relatively straightforward. So just real quick, kinds of collisions we talk about. A collision where kinetic energy is conserved is called a perfectly elastic collision. Now, in reality, this is an idealization. If two objects physically do touch, then some heat is going to be generated. Kinetic energy will not be conserved. But we sort of have this model where it's possible to have a quote unquote perfectly elastic collision where no kinetic energy gets converted into heat. But most real collisions are what's called inelastic, which means some kinetic energy is being converted into other forms, generally heat and sound. So in an elastic collision, kinetic energy is not conserved. And then a perfectly inelastic collision is one in which the two objects stick together after the collision. So a classic example of a perfectly elastic collision is I have two objects which are moving in opposite directions. They collide, and then they stick together and move as one afterwards. And those are kind of the main types of collisions we're going to look at least in terms of this upcoming celebration. So again, if I have a collision between two objects, those objects are going to exert forces on each other that are going to be hard to model in terms of how much energy is being generated as heat and so on. But the cool thing is, since they are internal forces, they don't affect the overall momentum of the system, and I can use conservation of momentum in collisions even when energy is not conserved. All right, let me pause for a second because that's a big point and just see if there's any questions. So in a collision, a physicist's first thing that they would think about is looking at conservation of momentum. It will always be conserved in a collision. The only time you could say energy is conserved is if you were told it's a perfectly elastic collision, which in reality doesn't really happen. Robert, question.
Yeah, going back to the explosion, I just kind of wanted to hear you repeat the part with the, I think you said the momentum was a vector, so all
Yes.
the particles that spread out will cancel each other out?
Yeah, so let's just take a simple example of, let's just say I have a 10 kilogram mass that's just at rest. And it's magically floating above the surface of the, whatever it is somehow. And there's some explosion which causes this thing to break off into two pieces. And let's just say, you know, one of these is 8 kilograms and the other one is 2 kilograms. And they're moving in opposite directions. So whatever caused the explosion. So one, if I were to just define my system as this box.
We can't see what you're writing.
Oh, it probably would help if I share the screen again. Share the screen, sorry about that. Okay, so let's just say I have a box, 10 kilogram box, which is on a surface. And because of something internal to the box, it explodes, it breaks into two pieces that move off into opposite directions. So one, if I define my system as the box, I do have external forces. And those would be, in this case, the normal force and gravity. But if there's no acceleration vertically, the normal force is just going to equal the force of gravity. So the sum of the external forces is 0. Now, conservation of momentum doesn't say there's no external forces acting. It says the sum of the external forces is 0. And remember, in terms of energy, if I'm looking at an isolated system, it means the total work done on the system is 0. Doesn't mean there's no forces acting, it just means the work done is 0. When I'm thinking about momentum, what I care about is the sum of the external forces 0? If it is, then what I can say is the final momentum of the system is going to equal the initial momentum of the system. So if my box is the system and it's initially at rest, it has no momentum, which means anything that causes an explosion is going to be an internal force to the system, which won't change the overall momentum of the system. So if the system started off with 0 momentum, it has to remain with 0 momentum. So if this 8 kilogram box, let's say, had a velocity of 10 meters per second to the right, it has a momentum of 80 kilogram meters per second to the right, which means the momentum of the other piece has to be 80 kilogram meters per second to the left. So if it had a mass of 2 kilograms, it would have to be moving to the left at 40 meters per second. Then if you notice, the final momentum of the system would be equal to 2 kilograms times a negative 40 meters per second because it's moving to the left, plus 8 kilograms times positive 10 meters per second because it's moving to the right, I get my total momentum is still 0. So if it starts off at 0, it has to end at 0. And just another quick little example dealing with all this, it's kind of cool to think about. If you ever shoot pool, so here is, you've got your 15 pool balls and you've got your cue ball. Let's say I define my system as the cue ball plus the other 15 balls. Now, each one of these has gravity pulling it down, the normal force pushing up, but the normal force will equal gravity. So if I define my system as the cue ball plus the 15 balls, after you hit the cue ball, now it has some momentum. It's moving, let's say, straight up. After the break, what I'm going to have is the 16 balls all moving in different directions. But if my initial momentum of the system points straight up, then that means my final momentum still has to be in the exact same direction. So when I go and I look at all these 15 balls moving in different directions, when I add these up like vectors, what I'm going to find is the total momentum before and after the collision have to be exactly the same. Now, if you try to model this using conservation of energy, extremely challenging, but momentum is always conserved in a collision. Okay, so let me do one more really great example problem and then do another question or two if we have time. So this is example problem 11A. And it says this: in the figure below, block 2, which has a mass of 1 kilogram, is at rest on a frictionless surface and touching the end of an unstretched spring of spring constant 200 newtons per meter. The other end of the spring is fixed to a wall. Block 1, which has a mass of 2 kilograms, is traveling at 4 meters per second when it collides with block 2, which is initially at rest. It says, when the blocks momentarily stop, by what distance is the spring compressed? So after this collision, these boxes stick together and they're going to compress the spring some distance delta x. The question is, what is that distance? And actually, here's the question I have for you. And I want to see if I can do this as a poll. Let's do a yes or no poll. The question is this: can I do this problem in one step? Can I say that the initial kinetic energy of the system, which in this case would just be the kinetic energy of block 1, can I say that equals the final elastic potential energy of the spring? So initially, block 1 is moving, block 2 is at rest, then they collide, stick together, compress the spring a certain distance. Can I say that the initial kinetic energy of block 1 equals the final elastic potential energy of the spring? Yes or no? What do you think? Take about 30 seconds. And somebody told me this: if you can't see the polls, if you can do Alt-Tab, that will open up all their possible windows and you can sort of Alt-Tab between the different open windows. Let's see, does that work? All right, anybody else want to go? Can I just use conservation of energy and say the final elastic potential energy of the spring equals the initial kinetic energy of the moving mass 1? What do you think? We got about 65% say yes, 26% say no. We got a little bit maybe. I'm going to give you another 10 seconds. All right, I'm going to end this poll, share results. And if you guys can see, can people see the results?
I can see it.
Okay, so I got about 68% say yes. In this case, 68% of you are not correct. Anytime two objects physically collide where they're physically touching, There will be some heat generated. There will be some sound generated. There's no easy way to model that. So when mass 1 collides with mass 2, some of the kinetic energy that mass 1 had is getting converted into heat and sound. I have no easy way of modeling that. So in any collision, the first thing you want to think about is using conservation of momentum. So this is actually a two-step problem. The first step is use momentum conservation. So use conservation of momentum to get the velocity after the collision. And then I can use conservation of energy to get delta x. So basically what's happening is mass 1 is colliding with mass 2. During the collision, some of the energy is getting converted into heat and sound, but I can still use conservation of momentum. So I can use momentum to figure out how fast are they both moving together after the collision. And now what I have are two objects that are moving with some kinetic energy, and all of that kinetic energy then gets converted into elastic potential energy. So how we would do this is, let's be specific for step 1. I'm going to define my system as both blocks. Again, there are external forces. I've got gravity and the normal force, but those balance each other out. So the sum of the external forces on this system is going to be 0, which means my final momentum is going to equal my initial momentum. If I have two objects, the momentum of the system is just going to be the momentum of each object added together. So in this case, my final momentum would just be m1 times v1 final plus m2 times v2 final. And my initial momentum would be m1 times v1 initial plus m2 times v2 initial. Block 2 was initially at rest, so v2 initial is 0. And anytime I have a perfectly inelastic collision, which is where they stick together after the collision, they're now moving as one. They have the exact same velocity. So I'm just going to write this as m1 plus m2 times v final. And that equals m1 times v1 initial. So initially, only block 1 is moving. Then it collides, they stick together, they move as one. Any force they exert on each other is an internal force, which means it's not affecting the overall momentum of the system. So momentum is conserved, but energy most definitely is not conserved. And in fact, you could calculate the total kinetic energy beforehand and the total kinetic energy afterwards, and you would see it's not. So in this case, I want to know what is the final velocity after they collide. So I'm just solving for v final is going to be m1 v1 initial over m1 plus m2. So what do we have for the masses? We've got, okay, I have it right here. We've got, move this down a bit. M1 is 2 kilograms. And it's initially moving at 4 meters per second. And then I'm dividing this by m1 plus m2, so 2 kilograms plus 1 kilogram. So what I have, 8 divided by 3, this is going to give me 2.67 meters per second. So after they collide, from conservation of momentum, now they're both moving at 2.67 meters per second. And one thing we need to sort of assume is the collision takes place very quickly. So now they're moving at 2.67 meters per second before the spring starts to compress. So now what I have for this situation is I've got 2 blocks connected to a spring. And now these blocks are moving at 2.67 meters per second. Now what they're going to do is they're going to compress that spring a certain distance, delta x. And in this case, again, if I define my system, now here I can define my system differently for momentum and for energy conservation. It doesn't have to be exactly the same. So keep in mind, if I want to include elastic potential energy, my spring has to be part of the system. If I want to include gravitational potential energy, the Earth has to be part of my system. For in this case, let's consider the system to be the blocks, the spring, and let's do the Earth. In which case, what would be my external forces? It would just be the normal force. And since the normal force is acting vertically and the displacement is horizontally, the normal force is not doing any work. And I could define my y equals 0 to be the elevation these blocks are at, and they're not changing their elevation. So my big energy equation basically says the work done by all external forces plus my initial kinetic energy plus my initial gravitational potential energy plus my initial elastic potential energy equals my final kinetic plus my final gravitational potential plus my final elastic potential plus any change in thermal energy. Now, quick little question. We've got 8 different terms: work, kinetic energy, gravitational potential energy, thermal energy. How many of these 8 terms survive? Take just 30 seconds. What do you think? Let me change colors here. Draw, let's go to green. And so 1, the only external forces are the normal force. It's not doing any work. The initial and final gravitational potential energies are 0 because I defined my elevation where they start and end to be y equals 0. There is no friction, so there's no thermal energy generated. When the spring is fully compressed, both masses are going to be at rest for a split second, so the final kinetic energy is 0. Initially, before the spring starts to get compressed, it's not compressed at all. And so what I end up with is basically the initial kinetic energy of the moving masses equals the final elastic potential energy in the spring, or 1/2 m1 plus m2 times v squared equals 1/2 k times delta x final squared. Now this v initial squared is the 2.67 meters per second that they have right after the collision. And let me just skip the step of doing the algebra. What you would find is my final delta x, how much the spring is compressed, would be 0.33 meters. Okay, I saw a couple chats here. Let me pull it up. So the heat released is not due to friction. Doesn't the spring compressing generating heat? Great question. So 1, the heat being generated is not because of friction. Just if I have 2 objects physically colliding, that collision will generate heat. And a great demo I would have done is if you take like 2 steel balls and you collide them together with a piece of paper in between it, you can actually get these 2 balls colliding together to burn a hole in the piece of paper. So the collision generating heat doesn't have anything to do with friction. There will still be heat generated even if there's no friction in the system. And then in terms of spring, if I were to take like a rubber band and stretch it and stuff like that, there would be some heat being generated. When we're dealing with ideal springs with Hooke's law, we're assuming that there's no heat being generated in the spring. We're also assuming the springs are massless. There's a few assumptions that real springs don't necessarily follow. Thanks, 200 newtons per meter. All right, let me stop this share. Let me open it up for questions. If there's no questions, what I'm gonna do is just do a quick little recap and then just sort of roll into office hours. So any questions on anything I've covered so far? If not, I'll do a little 5-minute recap and then open it up sort of for the office hours portion.
Joe, can you do one more example, please?
Yes, I'll tell you what, I will recap and then do another quick example. Let me see if I have, which one that I wanted to do. Okay, yeah, I have one more example I can do. So just quick little then recap of what I just covered today. Share, and let me just actually pull up some lecture notes. Actually, no, let's just go back to this. Okay, so today's big things are kinetic energy and momentum are related in terms of I want to look at the magnitudes. This is sometimes useful because I can use work kinetic energy theorem to figure out how much the kinetic energy changes. I can use impulse momentum to figure out how much the momentum changes. But oftentimes I want to know, given a certain who's got a greater momentum, which object has a greater kinetic energy, and so on. So the relationships are, I need to draw color here. Let's use orange. So kinetic energy is equal to momentum squared divided by 2 times the mass. Momentum is equal to square root of 2 mk. I also mention this because this will be useful in physics 4b. You'll use this equation quite often. Talked about collisions. In a collision, oftentimes energy is not going to be conserved. And in fact, any real-time 2 objects collide, some heat is going to be generated, some sound is going to be generated. However, there's an idealization where something is perfectly elastic. You have to be told it's perfectly elastic, and that means kinetic energy is conserved. Most real collisions are inelastic, which means some of the kinetic energy they had is converted into heat and sound. And a perfectly inelastic collision is one in which the objects stick together after the collision. Now, here's the thing. Even though energy is not going to be conserved in a collision, momentum will still be conserved, which is why it's so powerful. And we also use this all the time for explosions and things like that. So in an explosion, some kind of force causes these objects to fly apart. Well, if I define my system as, let's say, the firecracker, then whatever caused the explosion is an internal force, which is not going to change the overall momentum of the system. Okay, so let's do one more example problem. Example problems. This is, which one do I want to do? Let's do a problem 1128. And just so you know, this is sort of the level of the problems that you would see for conservation of momentum for the upcoming celebration. And let me just say, I know that it's different than the level of the homework problems. Talk about this, well, let me just touch on it really briefly. The level that you need to know physics 4a to move on to physics 4b and 4c and so on is sort of the level that I have for the homework problems. But just this new online paradigm, there's no way for me to test and quiz you doing problems that require multiple steps. And so all of the quizzes, the celebrations, the problems will be much more straightforward. And given the reality of everybody's situation, I'm really looking to have everybody pass this class. So the celebrations will be relatively straightforward, but the example problems that I'll do, the stuff that I have posted from old celebrations are going to be beyond the level of what we're going to be doing sort of for the quizzes. Okay, so this problem, 1128, and this is too thick. Let's go to black. Dan is gliding on his skateboard at 4 meters per second. He suddenly jumps backwards off the skateboard, kicking it forward at 8 meters per second. How fast is Dan going as his feet hit the ground? Dan's mass is 50 kilograms and the skateboard's mass is 5 kilograms. So, see if I can draw this, but the situation is, where's my thing? Draw. I've got Dan, who's on a skateboard, and together they are moving at 4 meters per second. Then Dan jumps backwards off the skateboard, sends the skateboard moving forwards at 8 meters per second. And the question is, what is Dan doing afterwards? Basically, how fast is he going as he hits the ground? So again, in these conservation momentum problems, first thing you want to do is define your system. So in this case, I want to define my system as basically Dan plus the skateboard. And what you want to do is define the system so that any forces that are causing objects to move apart or things like that are internal forces. So Dan exerted some force on the skateboard, causing the skateboard to fly forward, but that's an internal force, so momentum of the system is still going to be conserved. Now, I do have external forces, and those external forces, again, would be the normal force and gravity, but the normal force and the force of gravity in this case are going to be equal because the acceleration in the y direction is 0. So I can say that the sum of the external forces is 0, which means my final momentum is going to equal my initial momentum. And again, if I have two objects, momentum is just the momentum of one object plus the momentum of the second object. So in this case, and I'll just sort of do this problem here, what I'm going to end up with is, and let me just call Dan has a mass of 50 kilograms. Let me call Dan M1. And the skateboard has a mass of 5 kilograms. Let me call that M2. So initially, they're both moving together at the exact same speed. The initial momentum will be the sum of the masses times the initial velocity. And then afterwards, they're both moving at different velocities. So my final momentum is just going to be M1 V1 final plus M2 V2 final. And my initial momentum will be M1 plus M2 times V initial. I'm not writing this out as V1 initial plus V2 initial because they're both moving at the exact same 4 meters per second. So I know the mass of each object. I know their initial velocities. I know the final velocity of the skateboard. All I need to do is just solve for what is the final velocity of Dan in this case. So let me just skip a step of algebra. What you'll get is V1 final equals M1 plus M2 times V initial minus M2 V2 final over M1. So again, we have M1 is 50 kilograms, M2 is 5 kilograms, V initial is 4 meters per second, V2 final is 8 meters per second. If you plug in all the numbers, what you should find is that you get Dan's final speed. His velocity is a plus 3.6 meters per second. So one, this means that Dan is still moving to the right after he jumps off the skateboard. Keep in mind that velocity is a vector. So if you ever got the velocity to be negative, that means the object is moving to the left. Or again, keep in mind if I have two objects moving towards each other and I'm looking at momentum conservation, they have to have opposite velocities. If one thing is moving to the right, it has a positive velocity. The other thing's moving to the left, it has a negative velocity. Woo! All right. That is pretty much the end of chapter 11. So what I'm going to do is tomorrow, I'm going to just sort of review what you need to know for each chapter. It's chapters 8, 9, 10, and 11. And then I'm going to do a couple example problems just showing you the level of the problems that you can expect. And it's along the lines of the last couple problems I did, where the problems will be relatively straightforward, not going to be like the first celebration where you're turning in, you know, an entire page of calculations. These problems can all be done in a couple relatively straightforward calculations. So I am ending the lecture portion of this Zoom. And, oh, wait, I am ending the lecture portion of this Zoom, starting the office hour portion of this Zoom. What questions can I